6.3 definite integrals and antiderivatives. So we're going to get a lot of properties here for this section. And most of them, I'm going to be honest, are going to be relatively common sense, like to the point where you probably would understand them without me having to write them, but nonetheless, we're doing them anyways. Okay. So, all right, properties. 1, order of integration. So this says that the integral from b to a of f of x dx is equal to negative integral from a to b of f of x dx. So what that says is if I put a negative in front of the integral, I can flip the terms of integration and I'll get the same answer. Okay. And you're probably like, why? When is that going to be useful? There's a few sets of problems where they're going to give you an integral from, let's say, 5 to 7 of f of x dx, and they're going to tell you that that integral is equal to negative 3. But then in the problem, they say, then without giving you what f of x is, they're going to say, what is the integral from 7 to 5 of f of x dx? And you're going to have to invert it. Okay, so again, it'll make more sense then. But that just tells you can flip it as long as you take a negative out, okay, essentially. Or like put a negative out front of it. It's not really taking it out per se. But next one, 0. This just says that the integral from a to a of f of x dx is equal to 0. So essentially, if your interval is from 1 to 1, then it's got to be 0 because everything's going to cancel. We have the constant multiple. And this I'm going to write 2 different ways for you, but the first one, the integral from a to b of k times f of x, where k is just any constant number, dx, is equal to k times the integral from a to b of f of x dx. So that's just saying that any constant number that you have can be pulled out in front because that's not going to change. The only things that are changing when we're taking an integral are the terms that basically have x's in them or whatever our variable is for that given problem. The other way I can write this, which is kind of just self-explanatory off of that, but if I have the integral from a to b of negative f of x dx, I can, just like I can take, 5 out, I can take negative 1 out and have negative integral from a to b of f of x dx. And notice in this case, what's different about this one than the first one is that I made the first one negative and flipped the terms. Okay, this one had a negative in it that I took out, so it doesn't flip anything. So that's the difference there, in case you're like, why does that look different than the other one? The next one is the sum and difference property. And it is as it sounds. This says that if we have the integral from a to b of f of x plus or minus g of x dx, this is equal to the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. So it's just saying if you have 2 functions being added or subtracted, we can split them and do each of them individually instead of trying to do it all as one giant thing and you get the same answer. All right, this next one is called additivity. Another one of those things you probably never thought you'd hear that word before, or, But this says that if we have the integral from a to b of f of x dx plus the integral from b to c of f of x dx, this would be equal to the integral from a to c of f of x dx. So it's basically we have two intervals, but the endpoints of the intervals are the same, so we can do it from the entire interval and just do one integral instead of doing two separate ones.
You said what's the same?
So like the endpoint, so like this would be from A to B and this is from B to C. So since that like middle endpoint, if you will, is the same, we can just do it from the first endpoint to the final endpoint.
Gotcha.
So if it was like 5 to 7 and 7 to 9, we could just do it from 5 to 9. And it would be the same thing. The next one is the max-min. Probably wish you didn't have to hear those words ever again after the last chapter. Max-min inequality. If the max f and the min f are the max and min values of f on the interval a to b, closed interval, then the min of f times b minus a is less than or equal to the integral from a to b of f of x dx is less than or equal to the max of f times b minus a. So basically just telling you that there's a value between the min and the max that is in there, essentially. Kind of like, it's not, but kind of like the mean value theorem, which we will have a mean value theorem for integrals as well. That I'll give you in a few minutes. 7, this last one is called domination. This says that f of x is greater than or equal to g of x on the closed interval a to b. This implies that the integral from a to b of f of x dx is also greater than or equal to the integral from a to b of g of x dx. So this is an if-then statement. And another option of this, we could have f of x is greater than or equal to 0 on the interval a to b, implies that the integral from a to b of f of x dx is greater than or equal to 0. Which again, that one kind of just logically makes sense. All right, those are all the properties. We're going to have a definition and a theorem. So the average or mean value definition, if f is integrable on the closed interval a to b, its average or mean value on the closed interval a to b is AV of f, so it just means the average of f, is equal to 1 over b minus a times the integral from a to b of f of x dx.
You said ABF is average of F.
Yeah. The average value. All right, we had a mean value theorem for derivatives. Now we're going to have a mean value theorem for definite integrals. So I'm still going to call it MVT. So obviously you will know if you're dealing with integrals or derivatives. For definite integrals. If f is continuous on the interval a to b, you're going to notice this theorem looks very similar to the one that we had for derivatives. Then at some point c in the closed interval a to b, f of c is equal to 1 over b minus a times the integral from a to b of f of x dx.